Hi everybody, this is David Paul. Thank you for joining us today. So we're here to have a 1-hour webinar on water and wastewater minimization using electrodialysis reversal. I'll give a brief introduction. The whole thing will be about 40 minutes, then a 20-minute question and answer period. Ben Sparrow from Saltworks will give the details on their advanced EDR technology, and then we'll have 20 minutes for question and answers. So just type your questions into the question box and then we'll get to them at the end. This presentation is going to be recorded, so afterwards you can go to our website and you can view it again, or you can send other people to the website. Also tomorrow we'll send you a thank you email and there'll be a PDF of this presentation. So just so you know, Saltworks and David H. Paul Inc. do not have any kind of financial relationship, so we're not promoting this technology. We just want to make sure that our clients are aware of this technology and its application for both water and wastewater minimization. So I've been in water treatment for a very long time. I actually, my first EDR experience was probably in the early 80s in Florida. The largest EDR system in the world used to be at the county of Sarasota, Florida. Back then, the only time that EDR would win out over RO would be if you had a high silica groundwater, but today with the silica scale inhibitors we have, if we're looking at drinking water applications, most of the time RO wins. But now that we're getting more and more into wastewater treatment, finding that EDR is resurfacing. The person that's going to give us the most information is going to be Ben Sparrow. Ben also has lots of experience, real smart guy, and he is the founder and chief engineer and CEO of Saltworks. So we'll be hearing from him here in just a few minutes. So I'm just going to give a real brief run through of EDR. So that is just kind of a forerunner to Ben's more detailed. So electrodialysis, ED, was really the forerunner of EDR, but it just had too many scaling and fouling issues. Well, the EDR technology minimizes this by alternating the polarity of the electrodes. We're going to see that here in just a minute. Okay, so let's just get first into electrodialysis. So we're going to have a cathode. This is direct current, not alternating current, but DC current. So we're going to have a cathode that's negatively charged and anode that's positively charged. And then in between these electrodes, we're going to put basically ion exchange resin sheets. But in this case, we're not worried about ion exchange. We're really just wanting to transport cations across cation transport membranes and anions across anion transport membranes. So cations are positively charged ions. They can pass through cation transport resin sheets or membranes, but they cannot pass through anion transport. Same thing. Anions can go through anion transport membranes, but cannot go through cation transport membranes. So we're going to have alternating membranes between the cathode and the anode. Now there's going to be a spacer in between all these membrane sheets so that water can move between the sheets. So I'm just using these X's here to indicate that they're spacers, but from now on I'm not going to have the spacers. It's just going to make it more complicated. So your feed water is going to go through certain channels, and then it still will be feed water, but we'll call it rinse water for the other channels. So in the feed water, your cations, your positively charged cations are coming in, your negatively charged anions are coming in. You have an electrical potential. You've got this cathode negatively charged. You have this anode positively charged. So the cations are going to, whoops, sorry, went the wrong direction. So the cations are going to be attracted to the cathode. The cations can pass through cation transport membranes. So here, the cations can pass through the cation transport membrane, but they cannot pass through the anion transport membrane. Your anions are going to be attracted to the positively charged anode. They can pass through anion transport membranes, but they cannot pass through cation transport membranes. So what happens is that your feed channels then, your ions are leaving the feed channels, and we then call these the dilute channels. So the feed water, the ions are leaving, we call these the dilute channels. The other channels are where the ions are concentrating, and these are going to be the concentrate channels or the waste channels. So pretty cool technology, but it was fairly high scaling and fouling on water and wastewater. So the fix to that was electrodialysis reversal, in which case every 10 to 20 minutes the cathode is going to become the anode. So we're going to change the polarity every 10 to 20 minutes typically. So we're still going, I keep hitting the wrong buttons here. We're still going to have the cation transport and anion transport membrane sheets, exactly like we just saw with ED, but our dilute channels every 10 to 20 minutes are going to become waste channels, and our waste channel every 10 to 20 minutes are going to become our dilute channels. That way, as scalants and foulants accumulate on the membrane sheet, then once the valving swaps over and your waste channels become dilute channels, then they get cleaned off. But everything we talked about for ED is going to be true for EDR. So the cations go across the cation transport membranes. They're trapped in the concentrate channels. The anions pass out of the dilute chambers or channels and go into the concentrate channels. So no different, except for the dilute and waste channels are switching every 10 to 20 minutes. So as far as suspended solids, most of your particles in water have a net negative surface charge, so they're going to be attracted to positive charges. We also have scalants and organic material that can be attracted to one or the other of the membrane sheets. Well, the beauty of EDR is every 10 to 20 minutes, even though these foulants and scalants may be attracted to the membrane, well, 10 to 20 minutes later, we're going to swap the polarity, and that then is going to draw these materials off of the membrane. Ionics was the company that started this, like back in the 60s. GE bought Ionics in the 80s or 90s, I don't remember when. So when you see the word GE or GE Ionics, this is one of the original big stacks that they had. They were horizontal stacks. So today, because the patent has expired, there are some other manufacturers. The one that we're here to talk about is Saltworks. Now Saltworks does have a standard type of EDR, but the membrane sheets are vertical instead of horizontal, and also Saltworks makes its own membrane, so it has some specialty membranes that can do some things that are unique. So Ben is going to go into the details of this, but just to see that the membrane sheets here are vertical instead of horizontal. But the one we're most interested in, especially for wastewater, but also for real high recovery on the water side, would be this ElectroChem. So in this case, instead of just passing through one pair of cation anion membrane, actually going through two. And by doing this, you're able to go about 80,000 milligram per liter per pass. And so depending on the scaling potential of the water, maybe even going up to 150,000 milligrams per liter if it was like sodium chloride. So again, it's going to be a little different than just a strict EDR, but we'll let Ben give you the information on that. So this last slide of mine, we see that you could put one of these electrochems in front of an RO unit, and the EDR unit would soften the feed water so that it would be a scaling control technology for the RO unit. But then also you could run the brine through there, and it becomes a high recovery system. So enough of the intro. Let's go ahead and switch to Ben so Ben can give us the details. Ben?
Thank you very much for the introduction, David, and thank you everybody for joining. I assume that I can be heard, and I assume that my screen is shared. So for everybody's benefit, a brief introduction on Saltworks. We started in 2008 as an R&D company and technology company. And our approach to innovation has always been standing on the shoulders of those who came before us, taking good, solid industrial technology and tweaking it or reapplying it. So as we stand today, we are a manufacturer of ion exchange membranes and builder of ion exchange membrane systems. We also deliver reverse osmosis systems, often with our reverse osmosis partners. We do believe that reverse osmosis is the workhorse of the industry, and we try to apply it as broadly as applicable and use it to develop the lowest total cost of treatment trains for customers. And we're also a thermal company. We have a thermal system that we call the salt maker, which is a crystallizer. We will not go into that technology today. So we practice both membranes and thermal. Like many in the industrial water treatment business, we're growing quite rapidly. We had about 200% growth last year. Our customers are largely mining, industry, landfills, oil and gas. So they have challenging waters that they can either no longer put down the sewer or off-site discharge, or it's becoming quite expensive for them to put those waters in trucks, drive them away. So a lot of our customers are motivated by the economics of preventing off-site disposal. Other customers are motivated by debottlenecking processes and process improvements. Now, today we will get into the presentation, but really the meat of the presentation is four things that we call advanced EDR. Hybrids, dealing with organics, a technology we call the salt splitter, which is building from EDM, which changes water chemistry. And then we've also got a treat for you at the end on how we use these novel ion exchange membrane systems to pull out and destroy ammonia. So we refer to this as EDR 2.0, which is what we will talk about today. We will not speak about EDR 3.0, which is still proprietary to Saltworks and what we're working on in the future. So David provided an excellent introduction. Electrodialysis is a well-established technology, and we're leveraging its benefits and improving it and using it for different applications. One of the benefits that EDR has as a membrane technology is there's no pressure difference across the membrane. So water is flowing parallel to the membranes like wind flowing over an airfoil. This reduces fouling potential, unlike a pressurized membrane system such as ultrafiltration or reverse osmosis, where you impinge the membrane surface with organics. You can also desalt to any concentration with EDR. It's got a volume adjustment knob. So for example, you could desalt down to 3,000 milligrams per liter if you choose, or desalt further. So you can dial it in, unlike evaporation or reverse osmosis systems where they generally produce distillate or RO permeate. So you can adjust concentrations with this. And with these new membranes that were on the market initially, but we believe we've improved them, you can get selective and start to change water chemistry. David provided an excellent introduction. I won't go into it. Cations go one way, anions go the other way through their respective membranes. You reverse polarity of self-clean. Anybody can practice this. These patents are expired. Kudos, nevertheless, to those who came before us, particularly the fine people at Ionics that developed and commercialized this technology. Now, we often run into a very famous curve that was published by the USBR around 2003. And many in the industry refer to this curve. And I have to be honest, the curve is correct, but the technical understanding of it has been misapplied. This curve shows and informs that EDR should be more energy efficient, for desalting waters below 3,500 milligrams per liter. And reverse osmosis should be more energy efficient above 3,500 milligrams per liter. That is true, assuming both technologies are desalting to 500 milligrams per liter. So RO permeate at 500 and EDR treated water at 500 milligrams per liter. This curve is true under those assumptions. Now, where we practice, we tend not to use EDR to desalt to low levels, such as 500 milligrams per liter. So we call that EDR 1.0, the conventional application. This is where we practice. Now, there's been some good work actually out of MIT that has published curves around where EDR may fit and where RO may fit and where the EDR-RO hybrids start to come into place. And this is very much the same sort of message. Every water is different, every application is different. Nevertheless, EDR is more energy efficient if you do not desalt to a very low level. And we'll get into the hybrids and how you can leverage hybrids to achieve that. And then furthermore, EDR 3.0 and monovalent ion exchange membranes and changing chemistry, everything starts to change. Previously, high conductive waters have low conductivity behaviors. That is outside the scope of this presentation, but there's still lots of good innovation for the water sector coming down the pipeline. So, the curve is correct, the message has been wrong or misunderstood. In reference to an EDR-RO hybrid, this should help show this. So, we have feed water entering a system, and let's pretend or imagine that that feed water is 10,000 milligrams per liter. EDR is very effective and energy efficient at desalting from, for example, 10,000 milligrams per liter down to 5,000 milligrams per liter. All membranes tend to have a higher preference for removal of multivalent ions. This means that when you're desalting with EDR, you will tend to pull the troublesome actors out first. So you'll tend to pull out calcium and magnesium and sulfates, all of the scaling ions. They'll come out first. So in this example, we use EDR, or what we call ElectroChem, to desalt the feed to the reverse osmosis. We're lowering the salinity, but more beneficially, we're softening the water. So this is electrochemical softening upstream of reverse osmosis. Now the RO operates on reduced calcium magnesium sulfate load. In addition, there's a secondary benefit. The reverse osmosis brine can be recycled and provide the salt acceptor for the EDR system. So you end up concentrating the reverse osmosis brine at the same time. So with the EDR-RO hybrid, you get these two benefits. Electrochemical softening, get rid of lime, get rid of soda ash, get rid of the operational headaches, and you further concentrate reverse osmosis brine. What this looks like on a data basis, actually, pardon me, I'll go through the drivers first. So, when you're thinking about EDR and sizing EDR, try to remember these three things. If you use EDR to desalt to a lower TDS, your operational cost will increase, notably. So for example, below 2,000 milligrams per liter TDS, you can use EDR to keep desalting. However, your membrane flux must be decreased, notably. Your water resistance increases. All of this translates into more power consumption. It also translates into additional membrane area. So we find it highly beneficial to operate our EDRs above 2,000 milligrams per liter outlet, or EDR permeate, if you will. Now, when we're in monovalent mode, that all changes. In addition, with EDR, an interesting thing happens that increasing brine concentration really doesn't change costs that much. So there's a technical limit often for brine concentration. That's usually due to one of two things. One being scaling. You can still scale on a concentrate chamber of an EDR system. So that's one of your limits. If you do not run into the scaling limit, you'll eventually run into an osmotic flux limit, where the high concentration brine and the electroosmosis of water through the membranes adds more water to the concentrate then you're able to concentrate. Long story short, you level off on your concentration, you can't drive it any higher. We often find that the limit for electroosmosis is about 120 to 150,000 milligrams per liter. You can push it higher in ideal lab settings, but in a practical setting, you can use an EDR-RO hybrid to concentrate to about 120,000 milligrams per liter, assuming no scaling limits limit you first. The other big driver in EDR economics is the required salt flux. So when you're thinking about EDR, stop thinking about permeate flux or water flux through a membrane. You need to think about TDS flux through the membranes. And this is, again, one of the big drivers in cost. The more TDS change required, the more your cost is going to go up. So for example, if you wanted to desalt from 10,000 milligrams per liter down to 2,000 milligrams per liter, that might be price A. If you doubled your inlet TDS, you will almost double your price. Twice the membrane area, twice the energy. Of course, there are some economies of scale. So in summary, a greater change in TDS has a very significant impact on EDR capital cost and operating cost. You want to minimize that change. That's why we hybridize. Treating to a lower TDS also increases both CapEx and OpEx, but considerably OpEx. And brine concentration is really just a technical limit, has very little impact on cost, and we often push right to the maximum brine concentration and then back off slightly. So, some differences between conventional EDR and what we call our advanced EDR. Again, we are standing on the shoulders of others. EDR has been a fantastic technology. It's also had some problems. What people told us, and this includes some advice from those who originally helped develop the EDRs at Ionics, one of the issues was electrode fouling. You have a cation exchange membrane next to an electrode. Calcium can get in there. If you use sodium sulfate as your electrolyte, you now make calcium sulfate and you foul your electrode. People have managed that in different ways in the past. In China, they frequently use sodium chloride as the electrolyte, but that produces chlorine gas, which is a hazard. People also dose their electrolyte. We don't do that. We have a patented electrode blocker. So we electrochemically prevent any calcium or magnesium from ever entering the electrode. This means that we can use low-cost and safe sodium sulfate. No chlorine production, no need to acid dose. It becomes cheaper and more reliable. This also broadens our range of operating. We can operate on higher calcium magnesium loaded waters. Sometimes people use EDR with chemical softening up front. We really try to avoid that. One of our investors, one of the big oil companies, the vice president asked me one thing. He said, "Ben, get us off the drugs." You know, they really do not like softening. So it's a safer, more simple electrolyte, and we're leveraging all of the innovations of the past. When it comes to the membranes, some excellent membranes were developed. There are two types, heterogeneous and homogeneous. Heterogeneous are the original membranes. They are essentially ion exchange resins. If you're familiar with ion exchange columns, you take the resins, you grind them up into a powder, you disperse them with the glue, and you heat press them, and you cast them into something that looks like thin cardboard. They worked great. They're incredibly low cost. You can buy them today in China for $20 a square meter. The challenge is they have a rough surface. They're quite susceptible to fouling due to that. And they also have a much higher resistance than the second class of membranes, more modern membranes called homogeneous membranes. Homogeneous membranes are continuously cast. They are higher cost, but they offer some benefits that we'll get into. The other advantage that Saltworks believes we brought to the field of EDR is the mechanical design of our stack. It's modular. We're borrowing from reverse osmosis. Similar to reverse osmosis membrane cartridges that slide into a pressure vessel, we have EDR cartridges that go into a stack plate and frame. We also have a patent on a leak-free design. EDR stacks, as you tighten and compress them, they bow in the middle. This creates a chance for leakage between the various channels. Saltworks very simply developed a method to apply point forces on those critical points and compress those channels and maintain a positive seal. And then finally, and very importantly, all of the various processes, which include both in the stack, membrane arrangements, and outside the stack, the total process arrangement. So, ion flux ion exchange membranes. These are homogeneous membranes, which means they're continuous throughout. They're cast on a PET backbone with a novel polymer. And that novel polymer is cured. And what comes out of our membrane production machine is a ductile, flexible ion exchange membrane. That was one of our big value adds for ion exchange membrane chemistry. We developed a ductile ion exchange polymer. In addition, that ion exchange polymer is made with low-cost inputs without the need for pressure, temperature, and carcinogens. So it's more like making soup. This has been a real advantage for us. So the membrane's easier to produce. We can produce it at a lower cost. I would challenge any homogeneous membrane supplier to a cost bake-off. In addition, we do have these high multivalent ion transports, but really our true benefit is the mechanical integrity and the robustness of the membrane. It looks and behaves and feels very similar to vapor barrier, what you buy at Home Depot and put in your home behind drywall. So you can flap it around. With that robustness, it offers a longer life and it has a smooth surface. Now, what we've gotten into over the last number of years is applying coatings to our membrane. And we weren't the first to do this, and these coatings allow monoselectivity, enable you to get selective, but also, quite importantly, we've developed an anti-fouling coating that helps prevent organic fouling of the membrane. So we are a commercial company. We do R&D, but we also have commercial products. So we have 2 factories in Vancouver, and we also have an R&D station right on the water. We do customer training. Any customer who buys a plant, they can come and operate a similar plant on seawater at Saltworks. We have 24/7 customer support, quality assurance, and all of that is in place. Bench results, we do a fair bit of bench testing for clients. The bench results with electrodialysis scale up very well to full scale. It's a nice linear scale up. If the chemistry works at a small scale, it works at a large scale. You encounter mechanical challenges and other issues as you get to full scale, but the chemistry is the same. In bench work, if you ever do bench EDR work, what we often focus on is proving 2 things. Number 1, brine concentration. That's really the name of the game for the customers. Concentrate the brine as high as possible. So brine concentration limits. Number 2, flux. So how many membranes, what's the size, what's the energy, et cetera, et cetera. And of course, there's the requirements of treating water to certain levels, what's the output chemistry, et cetera, et cetera. But long story short, EDR scales up very well. We have automated pilots. Other people have automated pilots of different size, so these can travel around. We can do bench work at our site or send a CCAN size pilot out to a site to run it in the process. We'll now get into the applications, the hybrids in a bit more detail, organics, removal, and changing water chemistry. So we've already gone through this. This is the EDR-RO hybrid, picture of a pilot plant, high level, soften the RO inlet, and concentrate the brine at the same time. In this system, you're not changing water chemistry, which means you can still run into the same scaling limits that you would run into in any other system. So calcium sulfate often will limit recovery of this system. You can push an EDR-RO hybrid to higher calcium sulfate levels in the brine than you can with reverse osmosis alone. You need to use aggressive antiscalants, just like reverse osmosis, and you need to practice electrodialysis reversal, just as David touched on. That enables you to go a bit higher. Now, one thing that this system doesn't do, or the EDR system doesn't do, is it does not remove silica and it does not remove boron. So that means you need this RO downstream if you want to remove silica and boron. In addition, this system does not remove scaling limits associated with silica. So silica can accumulate in the RO reject loop. And we often find that the recovery limits of an EDR-RO hybrid are governed either by calcium sulfate or silica. but we also frequently find that it does offer these benefits of reducing brine volume and removing softening, chemical softening. Here's an example of how it electrochemically softens. Ion transfer rate of different ions. Long story short, higher transfer of divalent ions such as calcium, sulfates, etc. than the monovalents. Here's a data curve of what it looks like. So the black line at hour 22 is when the reverse osmosis, is when the EDR unit is turned on. So at hour 0, the red line is the brine or the concentrate. The blue line is the reverse osmosis feed. At hour 20, bang, the EDR is turned on. You can see that the RO feed is desalted. Its conductivity lowers. And again, we're largely softening it, but also pulling out some monovalents. In addition, the brine is being concentrated until you reach a steady state brine concentration and run at that level. So we reach steady state around 175 hours. Now the concentrate is charged. You keep running at that level, discharging concentrate, making up your concentrate volume with whatever fluid you may have. Preferably, we use the EDR outlet flow. The green line, we sometimes use a 3-stack compartment where we increase the concentration in multiple stacks. David briefly touched on that. I won't go into much detail. But if EDR was a ladder with 2 rungs, you can only transfer ions across a membrane concentration difference of about 60 to 80,000 milligrams per liter before you start to run into problems. So that would mean EDR can only concentrate 60 to 80,000 milligrams per liter. Saltworks has a patent on this. We added a 3rd rung to the ladder, so you do it in 2 steps. You concentrate 60 to 80,000, and then you further concentrate 60 to 80,000 again in a single stack. That's what we do in our transfer chamber. So we'll now get into produced water, what we call our produced water desalter. We've just started doing some work on municipal wastewater centrate with the same system, and it's proving to perform very well. Most of our experience basis is, however, on oil and gas produced water. We've been working on this with 4 of the world's biggest super major oil companies. If you read The Economist and if you believe what they say, the super majors, not the national oil companies, not Saudi Aramco and not Venezuela, but the super majors, they believe that some 40% of their oil production moving forward is going to come from water flood enhanced oil recovery. So here's some water flood enhanced oil recovery water. We ran experiments with 4 of these companies at various different times. Only the salts flux through the membrane. We're able to adjust the produced water salinity back down to their optimal range for re-injection. We include our hydrocarbon resistance membranes. You can see a picture of what the water looks like. We did pilots both with and without pre-treatment, and to our shock, the results were the same. We have some special art in our stack, thicker spacers to prevent plugging due to particulate, and again, the coating on our membrane. The produced waters we've tested, they have a nominal inlet TDS of anywhere from 15,000 to 45,000 milligrams per liter, and then again, we pull it down to that optimal reinjection limit of about 2,000 milligrams per liter. The oil companies, they like a little bit of salinity in their water when they re-inject it. It helps push out more oil. And they also, there's some tuning of salinity of certain ions that you can do as well. Now, the alternative to using EDR to do this would be reverse osmosis, and I'm one of reverse osmosis' biggest fans. I think if you look at that water, you can tell that it would require a fair bit of pre-treatment, which adds cost, complexity, and if you're on an offshore oil platform, that can take up a lot of space. So you can do this with a single unit process, such as our ElectroChem stack, and some nominal pre-treatment to get the big particulate out up front. Now, this is small pilot bench days come 2020. Expect to see more of this out in the field. This is long game for Saltworks. This is also long game for the EOR producers. Some chemistry. So again, no pre-treatment. You can see the produced water chemistry here. There's, well, this one 5,000 to 40,000, then desalting down to 1,000. And you can see lowering hardness, leaving some chlorides in, and lowering sulfate as well. So we'll now get into our salt splitter system, which is very much standing on the shoulders of 2 incredibly bright gentlemen. The concept is called Electrodialysis metathesis, or EDM. The concept is to change low solubility calcium sulfate permanently into high solubility fluids, sodium sulfate and calcium chloride. And I'll come back to that. So this concept was first presented by a Japanese gentleman, Hamano, in 1993, specifically to changing the water chemistry. And then Dr. Davis from UTEP very much further improved on it through ZDD Corporation. And Saltworks is continuing that work. We're continuing to improve on it. And really the fundamental concept is calcium sulfate has a low solubility. Call it 2,000 milligrams per liter without antiscalants. Sodium sulfate, calcium chloride are highly soluble, well over 100,000 milligrams per liter. So split the calcium sulfate into two compartments, make sodium sulfate, make calcium chloride. They're now both highly soluble. So with this, again, it's no softening, no lime, no soda. It's a membrane system, it's a hybrid. And most people on this call will know that membrane systems are often an order of magnitude lower cost than a thermal system. We're a thermal system builder too. So we often try to keep clients in the membrane world to keep their costs down. You can achieve extreme recoveries. We've gone through a very successful pilot that's now being expanded with one of Canada's major mining company, who actually also ended up becoming an investor in our firm due to this success. So a gypsum saturated water that conventional reverse osmosis without softening could achieve 40% recovery. With softening, both lime and soda could achieve 70% recovery. The membrane system right now is running at 96% recovery with saturated gypsum on the inlet. So everybody on the project has seen that as a huge success. And again, you're changing water chemistry, as this diagram shows. You're moving the sulfate and the calcium into two different process units, two different pipelines. You're separating those brothers and sisters once and for all, and you're giving them a new brother or sister, sodium or chloride, so they're highly soluble. Now, similar to the other EDR-RO hybrid, this does not solve the silica problem. Here's some representative water chemistry from the pilot. So there's the inlet. You can see the water chemistry, and then what we achieved with the brine. So well over 120,000 milligrams per liter for brine, extreme recovery, starting to get into the territory of evaporators. Again, we also make an evaporation system. Now, a little bit of a treat at the very end. We've developed a third product line. We've adjusted our membranes and tuned them to pull out ammonia. Ammonia is becoming more and more important in the wastewater and the industrial sector. It's, if you don't know, it causes challenges in our aquatic environment. Ammonia is wonderful for farmers. It's a brilliant fertilizer, but it also fertilizes rivers, lakes, and the ocean and creates algae blooms and all sorts of other problems. If you were following the news, there were over 30 whales found dead on the west coast this year, all of a sudden, and the suspected culprit was an algae bloom. Whether or not that was caused by environmental things that could have happened anyway, or increased ammonia being discharged from North America. So we've been working on ammonia and tuning our ion exchange membranes to pull out ammonia. What we do is again, our same stack, our same EDR system with a slightly different membrane. There's some chemistry that occurs. We pull ammonia out, we convert it to ammonium. You then have two options of what to do with that ammonium, or three options. So this is a two-stage system. The red line is the source water with the ammonia. We pull the ammonia out into a closed-loop ion capture fluid, the green line. It's now ammonium X. X could be sulfate, could be chloride, could be nitrate. The regenerator is an add-on. It's an option to burn the ammonia off electrochemically as nitrogen gas and destroy it once and for all. The air is 70% nitrogen, so it's a safe nitrogen gas. All sorts of testing have been done to confirm the full conversion, lack of buildup of nitrates and what have you. We've been running two small pilot systems, one on a very strong industrial landfill leachate, and the other on wastewater treatment plant centrate. So using this ammonia splitter to pull out approximately, it depends, anywhere from 20 to 70% of their ammonia load and lower the ammonia load on their water treatment plant. So here are your three options of what to do with the ammonia once you pull it out. Option one, it is the most expensive. Electrolyze it to nitrogen gas. It requires the highest amount of energy, but then the liability is gone once and for all. You've permanently destroyed the ammonia. Now, you can get cute and you can make fertilizer, you could make ammonium sulfate. You can usually only concentrate this to about 7.5% by mass, so it's not industrial ammonium sulfate concentration, but it may or may not help if there's a blending facility nearby. Where it gets very interesting is making ammonium nitrate. Many wastewaters have these two troublesome actors in them. They have ammonia and they have nitrate. If you put the two together, all of a sudden now you have a high value compound. Ammonium nitrate is one of the highest value fertilizers. Unfortunately, it's also used by people for other means, but I won't get into that. So some data. If, for example, you were to put an ammonia splitter on a wastewater treatment plant on centrate, you can pull ammonia out of the centrate, lower the mass load in the centrate, which is recycled to the front end of the wastewater treatment plant. You now have less ammonia circulating. It's easier for you to meet your discharge limits. So with that, we welcome any questions. We will be able to speak about the technology that's released. We will not be able to speak too much about what we're working on, but nevertheless, for customers on the call, I encourage you to contact us at projects@saltworkstech.com. Every application is different. Feel free to threaten us with water chemistry, and we will threaten you with a desktop study to explain performance, expectations, cost, etc. Thank you very much. Over to you, David.
Okay, thank you, Ben. Excellent presentation. Learned a lot. Appreciate that. So we are in, we're right on time. We're at the question and answer period. If there are any questions for me, which I'm not expecting, then I could answer them now. Otherwise, I think we'll just go right back to Ben, because I'm sure probably all the questions are going to be for him.
Yep. Okay, great. So the question is, can this process be used to provide zero discharge system for someone trying to remove TDS from their wastewater? Specifically, they have a client who's trying to reduce TDS by the POTW they discharge to. So POTW, it basically means the sewer or a wastewater treatment plant. So somebody's trying to pull out TDS. Now, the answer is that EDR is a very good application for pulling out TDS. You can think of it as an ion pump. It'll pump ions out of your wastewater. But the question becomes, where do you put those ions? So you can pull them out of the wastewater and you can concentrate them to, again, about that 120,000 milligrams per liter mark, assuming no scaling limits. But I wouldn't call it zero discharge, because you still have this concentrate or brine that you need to manage. And that's where another option comes into play. So, for example, you could put that into a truck and drive it away to a deep well. You could further concentrate it on site using an evaporator. There's many excellent companies that make evaporators. Veolia, GE, IDE, they all make evaporators. But you will still, long story short, you will still need to deal with that salt. You will just significantly reduce the volume and the mass. So the second question is, can I give a brief description of the crystallizer? It is really, I'd love to. It's outside the scope of this presentation. I'd encourage you to go to our website, saltworkstech.com, and you'll find some material on that. It's essentially a multiple effect crystallizer built from fiberglass, built for non-scaling. It was developed with Suncor, one of Canada's biggest oil companies, and some other companies. We had some excellent input on it to make a simple, reliable industrial crystallizer that's easy to maintain. Other question, how does EDR compare to electrocoagulation for ion removal and treated water final cost? So EDR and electrocoagulation are two very different technologies. Electrocoagulation uses a series of metallic plates. I'm Canadian, so we pronounce it aluminium. Aluminium or iron plates, you then, these iron and aluminum ions, there you go America, the aluminum ions float around and they coagulate stuff. That stuff may be heavy metals, it may be oils and grease, and then you clean out that stuff. So electrocoagulation is an option for pre-treatment for certain waters. Electrocoagulation does not remove TDS, and in fact it can increase TDS in some applications. So EDR is a TDS remover. Electrocoagulation is a heavy metals, oil and grease remover, in my view. Others may have different views. Another question, Can you discuss a bit more about the RO reject going through your system? What does it do? So I'm sorry if I went over that too fast. In EDR, you have a minimum of 2 channels. Channel 1, you're desalting. You're lowering the salt content. Channel 2, you're increasing the salt content. We call it the salt acceptor. It's where you need to push the TDS. In the EDR-RO hybrid, we recirculate the RO brine through the EDR and we use it as the salt acceptor. Now, you still have the same theoretical recovery limits as reverse osmosis when it comes to scaling. If gypsum is going to form and crash out, in theory, it'll do so in an EDR at the same point it would do so in an RO. However, the benefit of using EDR for very high gypsum waters is you have the EDR reversal, which enables you to ride closer to that ragged edge of gypsum formation because you can recover from it. You can electrochemically backflush the membranes, whereas you cannot backflush an RO unit. If that didn't clarify the question, feel free to contact us after, projects@saltworkstech.com. What is the size of the systems you have deployed at present in terms of flow rate? We have a series of small commercial systems, so using the modular stack. So for example, the largest system, 50 in EDR, 50 cubic meters per day. Our clients right now are not motivated by size. Where we work best is solving the big problems that they're facing and helping them to maintain their consent to operate out past 2020. So no way we are like GE, nor do we have their balance sheet. If somebody wants a conventional EDR system, GE is the place to go shopping. They have an Ionics. They've built tremendously large systems. They can provide that sort of scale. The value Saltworks provides is more advanced technology and options around changing water chemistry. Does ElectroChem produced water desalter work for both dissolved and free organics? So, organics do not pass through, should not pass through ion exchange membranes. So, we've done a whole pile of testing and we're finding that our EDR system and the membranes are tolerant to both dissolved and free organics, including free oil. You do have to be careful. So first off, high molecular weight organics are not a problem for the membranes. They just flow right by the membrane. Charged mid-molecular weight organics can lodge in a membrane surface. You practice reversal, ionic reversal, to dislodge them. We also have our coating, which helps dislodge them. My greater concern with organics in EDR isn't the membrane, but it's, call it electrocoagulation of the organics inside the stack. You can form a gel inside the stack, and that's where you need to be careful, and that's where some of our art is required. What are the flow rates for the modules? So one stack has a maximum hydraulic flow rate of 150 cubic meters per day. You can go less than that by removing pages from the book, but maximum 150. Higher than that, you need multiple modules. Here's a question of cost. Cost divided by 1,000 gallons equals 30. I'm sorry, I do not understand that question. And whenever quoting cost for EDR, you also need to quote TDS. So TDS is a bigger driver on hydraulics for EDR. So I'm sorry, to whoever asked the question, email projects with your application and we'll get you an answer. Looking at the ElectroChem hybrid, it sounds like works much better with anti-scale treatment versus softener pretreatment. Yes, absolutely. So we do not use softener, but we do use anti-scalant. And you need to be careful in that anti-scalant because EDR and reverse osmosis use different anti-scalants. Where would you define as your niche or sweet spot? Thank you for the question. I would say multiple. So we're not a silver bullet, nor are we a one-trick pony, nor do we fit into any box. We often get confused. Clients don't know if we're a technology developer, a manufacturer, an engineering company, or a service company. We're all of the above. Our niche or our sweet spot is solving difficult problems. Contact us. We'll be honest and tell you if we can't. We have an excellent group of other vendors that we work with that we can recommend you to if we're not a fit. How how low can ammonia be reduced to practicality with the ammonia splitter? So the ammonia splitter can reduce ammonia content well below 1.9 milligrams per liter, which is the US EPA limit. However, the better way to think of the ammonia splitter is as an ammonia pump. Its economic sweet spot is to remove approximately 75% of your ammonia load. If you try to remove 75% of your ammonia load, you can do it, but your chemical consumption and your costs will go up. And in my view, there are other technologies better than our ammonia splitter for polishing that final 25%. So in my view, the best applications of the ammonia splitter are pulling ammonia load out of a circulating system, such as a wastewater treatment plant centrate loop or other types of loops. If you have, for example, ammonia coming out of your pipe at 30 milligrams per liter and you want to pull it down to 1 milligrams per liter, that's a brilliant application. The ammonia splitter can do that. If you have 3,000 milligrams per liter ammonia and you want to pull it down to 1, I would not recommend that. I would recommend ammonia splitter with a hybrid. Let the ammonia splitter do 75% of the work and let another technology do the final 25% of the work. Has EDR been used on RO concentrate rather than pretreatment? Great question, yes. And the best work for this is coming out of China. It's frequently done in China where they just put RO concentrate directly into EDR and desalt it further. There's some benefits. Hydraulically, you have lower flow. Hydraulically, your stacks become smaller. There's some drawbacks. You don't get the electrochemical softening upstream of the RO. Can EDR be used for ultra-pure water production? The answer is yes, but I would not. There's no need to have a titanium coat hanger. There's better technology for ultra-pure water, specifically EDI, electrodeionization, which is where you put resins between the membranes. For EDR, what typically is the DC voltage and current expected, and does it vary according to the system's capacity? Yes, absolutely. DC voltage per membrane cell can be anywhere from 0.1, 0.2 volts all the way up to 2 volts. The voltage depends on your brine concentration and the resistivity or conductivity of your water. The current also varies. We'll run systems, I'll give you current density, anywhere from 600 amps per meter squared all the way down to 5 amps per meter squared. Higher current density equals less membrane area equals smaller system. However, sometimes there are these things, sometimes there's something called a current limit. I won't get into the details. You cannot run above the current limit. Otherwise, you split water, and you don't want to do that inside a stack. What's the next question here? Will ammonia removal technology also remove amines and various types of wastewater stream? Forgive me, I'm just a dumb mechanical engineer. I'd have to ask our CTO, who's a real chemist. However, I don't think so because we really tuned it just to target ammonia. Nevertheless, if you've got a problem or a project, contact us. We can take a look at it. There may be a solution. How sensitive is EDR membrane to common water treatment chemicals such as bleach or common coagulants and floaculants? This is a good question. Thank you for mentioning it. So our EDR membrane is quite is insensitive to oxidants. So you can run it on chlorinated water. There are some limits. Again, I'm not the chemist. I need to get those, but you can chlorinate the water. Other coagulants and flocculants, we'd need to check that. I need to check with somebody smarter than me. Possible to retrofit existing EDR to become EDR? Anything's possible. You would need to change the electrodes. In EDR, both electrodes need to be reversible, so they're often made of titanium and coated with a noble metal. Whereas conventional ED, you often have a stainless steel electrode on one side. And that was the last question. Thank you very much for everybody who attended. Again, contact us at projects@saltworkstech.com for specific applications. We love new applications. Thank you very much.
If you want to know more information or obtain more information on other technologies, other membrane technologies for water and wastewater minimization, we have a 3-day seminar on this in April in Albuquerque, and I will be instructing that. This came out of a 1-year research project for the Electric Power Research Institute looking at current and emerging membrane technology. So if you're interested in that, go to our website and get the details. So thank you so much. Have a great rest of the day and great week. Bye-bye.